Hello students, welcome to the class of Control System 1. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. This is our second video lecture on the bode plot. In this video, we will discuss on some numerical problems of bode plot. So, this video contains the introduction, the scale of the bode plot, some examples. Now, the main attraction of bode plot is that it can be produced and modified by using pencil and paper methods. The open loop transfer function represented in factored form is approximated by a number of asymptotic straight line, that means one for each factor, which may be added graphically to produce plots accurate enough for the most of the design studies. Now, the bode plot is used to determine the gain margin and the phase margin for analyzing the stability of the closed loop system. And now, some computer programs are also available to produce the accurate bode plot of open loop transfer function. So, the design problems have become much easier today. And in this video, the traditional method of producing the bode plot based on the asymptotic approximation to the various elements within the loop and then cascading them all for the overall open loop transfer function has been described. So, here the bode plot is actually the graph of frequency response of a system, and it consists two plots. One is the magnitude plot and another is the phase plot, and both the plots x-axis has been represented by the angular frequency in the logarithmic scale, and for the magnitude plot the y-axis represents the magnitude in the linear scale, and it is also in dB, and for the phase plot the y-axis represents the phase angle in degree. And if we add the different part of individual terms, it will give the complete bode plot. And after getting the bode plot, we can find out the stability of the system using the phase margin and gain margin concept. That part we will discuss on the next video. In this video, we will only discuss how to draw the bode plot. So, before starting, we have to keep in mind two things. One is the magnitude of the open loop transfer function that will be expressed in the decibel unit, and to convert this we will use this formula. Magnitude in dB is 20 log g of j omega h of j omega mod, and the phase angle of the open loop transfer function will be expressed in degree, and base of that logarithm will be 10, and the frequency of the bode plot are plotted against the logarithmic frequency, and every frequency axis represents a power of 10 times of the previous value, that means the decade. And to convert the bode plot, measure the phase shift in, actually it is measured in degree, but also radians can be used, and for magnitude plot we will convert it into dB by using multiplication with 20 log of the value. So, these are the scales on the bode plot. So let us take an example. Here we will draw the bode plot of a given open loop transfer function that is given as 200 into s plus 10 by s into s plus 5 into s plus 20. So first step, we will convert this pole 0 form into time constant form, because to find out the corner frequencies we need to use the relation omega is equal to 1 by tau. So it will be simple if we convert the form into time constant form. So first step, we will convert the pole 0 form into the time constant form. So to conversion, we will take common 10 and here 5 and then 20. So it will give 20 into 1 plus 0.1s by s into 1 plus 0.2s into 1 plus 0.05s. So there is a pole at origin. Next, we will convert the sinusoidal transfer function. That means we will put s is equal to j omega. So in this relation, I have just put s is equal to j omega and find out this relation. Next, we will have to find out the starting point. That means the point from where the graph will be started. So for the starting point, it will be dependent on the pole at origin and this constant value. So here it is 20 and this is omega. So the starting point will be dependent on this 20 and omega value, and the formula is 20 log of 20 by omega. Now what will be the value of omega? This omega will be the value, whichever value you are considering at the first line. If you start from 0.001 and then 1 decade, then you will put 0.001 instead of this omega. But I have used here 0.1. That's why I have put 0.1 over here, and the final answer is 46 dB. So for this problem, the graph will start from the 46 dB. And next, we need to find out this table, and this is the most important. That is, first we need to find out the corner frequencies. And corner frequencies are nothing but the frequencies where two different slopes are made together. And it can be found out by using the omega equal to 1 by tau formula. And tau is the time constant. So for each term, we will find out the corner frequency, and for each factor, we will find out the slope for that factor and the net slope. So there are total 5 terms, but one thing you have to remember that these factors, that means these are factors, these 5 are factors, and these 5 factors will be written by increasing the corner frequencies. Because if we consider the graph, then in x-axis, omega is varying from 0.1 to any values, or 0.001 to any values. That means to the right hand side, the omega value is increasing, and that's why we have to write the corner frequencies in the increasing order. So first, we will identify for each factor what are the corner frequencies. So first, take this term 20. So for the 20, there is no imaginary part, so there is no corner frequencies. And here there is no real part, so here also there is no corner frequencies, because there is no real part or the imaginary part over here. Now next we will consider this term. Here the tau is 0.1. So when tau is 0.1, then 1 by tau will be 10. So the corner frequency will be 10. And for 1 plus 0.2s, here the tau value is 0.2. So the omega value will be 1 by 0.2, that is equal to 5. And for this one, the value is 20. So now we have to rearrange the terms according to the increasing order of the corner frequencies. So first we will take the term 20 and 1 by s or 1 by j omega in the equivalent sinusoidal transfer function form. So first factor is taken as 20, then 1 by j omega. Then we will write down the corner frequencies first. That is, the minimum one will be written as first, that is 5. That means for this term. The next corner frequency for this term is 10, and for the third one the corner frequency is 20. So 5, 10 and 20. So 5 is the corner frequency for the factor 1 by 1 plus 0.2 j omega. And for 10 the factor is 1 plus 0.1 j omega, and for 20 this 1 by 1 plus 0.05 j omega. Now the factor and corner frequencies are written. Next we need to find out the slope contributed by each factor. And as we know from the previous lectures and the previous videos, I have shown that why the slope for this 1 by j omega is equal to minus 20 and why this slope is 0. So two things you will keep in mind, that is for any constant values there will be 0 slope, and the value at the denominator, if a term is located at denominator, then the slope will be minus 20 dB per decade, and if it is located at numerator then it will give the slope of plus 20 dB per decade. So this 1 by j omega term is located at denominator, this j omega term, so the slope is minus 20. Next, this term is also at denominator term, that is it represents a pole. So for a pole the slope will be minus 20. It represents a 0, and for a 0 the slope will be plus 20, and again it represents a single pole, then it will give the minus 20 dB per decade slope. And the unit of this is 20 dB per decade. Next we will find out the net slope. Net slope will be nothing but the summation of the previous slope and the current slope. That means for the first line the slope contributed by each factor is 0, so net slope will be 0, and for the next line this 0 plus the current slope, that is minus 20, gives us minus 20. And for the third line, this is previous net slope is minus 20 and the current slope is minus 20. So summation of these two becomes minus 40. And we will complete this net slope like this: minus 40 plus 20 gives us minus 20, and minus 20 minus 20 is equal to minus 40. So this is the net slope, corner frequency and the factors. Now we will plot the bode plot for each factor, and the overall cascading form is the bode plot of the open loop transfer function. So this one for the magnitude plot. Now we will go to the phase plot. So this for this phase plot I have put the formula from here, that is for 20 there is no angle contribution. For this numerator term the angle contribution will be plus tan inverse 1 by 0.1 omega divided by 1, and for this one it is minus 90. For this one minus of tan inverse 0.2 omega, and here it is for minus of tan inverse 0.05 omega. So that is written here: minus 90 minus tan inverse 0.2 omega minus tan inverse 0.05 omega plus tan inverse of 0.1 omega. Now we will vary the value of omega from 0.1 to infinite. I have not considered the 0 value because my graph has been started from 0.1. So I have put the value 0.1 and up to infinity. Now for a phase plot it will be more accurate if you draw the magnitude plot first, and then you will find out the gain crossover frequency, that is the point where the magnitude plot intersects the reference line, that is gain crossover frequency, and you will take that gain crossover frequency value over here. So in this problem I have not considered the gain crossover frequency and phase crossover frequency to measure the phase margin and gain margin. That's why I have not considered here, but you can use this, so it will be more accurate. So for each values of omega I have find out the angle of jj omega, hj omega. So these are the this is for the phase plot. So next, first we'll start the magnitude plot. So this is a similar graph paper of 5 cycles. And I have told that I have in x-axis it will represent the log omega, whereas in the y-axis for the magnitude plot it will represent in dB, and for the phase plot that will be represented in degree. So here the first line is 0.1 because omega is starting from this point. So it is 0.1. Then if you look carefully, then you can see that this point is 0.1, then this 2, it becomes 0.2, then 3, 4, 5, 6 like this, and it will increasing into 10. That means 0.1 into 10, that means 1 decade. So from 0.1 to the next cycle, that is 1 decade. And again from 1 to the next cycle, that is multiplied by 10, 1 into 10, it gives us 10. So it is the another decade, and so on. So here there are 5 decades, 0.1, then 1, multiplied by 10, that is 10, then multiplied by 10, it will be 100, then 1000 and 10,000. Now, we know that why it is 0 dB. I have marked why 0 dB as a reference because in the Nyquist you have seen that -1 plus J0 point was the critical point, and we can find out the stability of the system by using this -1 plus J0 point, because if we increase the value of gain K, then there is a tendency of the polar plot to encircle the critical point -1 plus J0 as the gain is increased. And the closeness of this open loop transfer function to the -1 plus J0 point can be used as the measure of the margin of stability. And that's why when we are converting the magnitude into dB, so in that part, that -1 plus J0, that means mod of G, if we consider the characteristic equation, mod of GH is equal to 1, and now we are converting it into dB, that means log of 1, and log of 1 is 0. That's why 0 dB is reference for the magnitude plot, and for the phase plot, -1 plus J0 point is located at -180 degree line. That's why for the phase angle, -180 degree line is the reference line. So first I have marked this 0 dB line by a straight line. So this one is 0 dB. And then I have considered that each small box, you can see the small box over here, and each small box represents 4 dB. So after 5 small boxes, I have marked 20 dB, then 40, then 60, then 80 dB. Like this. So for the magnitude plot, I have considered one small box represent the 4 dB. And according to that, I have marked the values. That is 20, 40, 60 and 80 dB. So first we will plot the magnitude plot. And our starting point was 46. So if this point is 40, then we can easily identify which line will be, this point will be 46. So this is the 46 dB, and the graph will be started from here, and here the value is 0.1. That's why I have put for the starting point calculation, I have put omega is equal to 0.1. That's why it comes to 46 dB, and it will be started from here. So now from this, you need to consider this table. So here we will put the factor 20 and 1 by j omega, and here the net slope is -20 dB per decade. So from the starting point, the graph will start with the slope of the -20 dB per decade, and it will go with the same slope till the next corner frequency comes, because at the corner frequency the slope will be changed. Before that the slope cannot be changed. So first it will start from the 46 dB, and then with the slope of -20 dB per decade, and it will go up to 5, that is the next corner frequency. So this one is the 46 dB. Then we have to draw -20 dB per decade. So -20 represents you have to go downwards. That is for -20 dB that means total 5 boxes, because one box represents 4 units. So I have gone downward direction, total 5 box, then 1 decade. As this line is 0.1, then 1 decade means 0.1 into 10, that represents 1. So then I will join these 2 points, and this slope is minus 20 dB per decade, and the slope will continue up to the next corner frequency 5. So this one is 5. This one is 1. The next 2 represents 2, 3, 4, 5. So up to 5, this is the minus 20 dB per decade slope. And this is the first corner frequency omega C1, and it represents the 5 radian per second. So this is the first corner frequency. And after the first corner frequency, the slope has been changed into minus 40 dB per decade. And this minus 40 dB per decade this slope will continue up to the next corner frequency 10 radian per second. This is the next corner frequency. So minus 40 dB per decade will go up to 10 radian per second. So from this we have to go downwards, total 40 dB, minus 40 dB, that means 40. 40 means each box represents 4 units, so 40 means total 10 boxes. So I will go downward at 10 box and then 1 decade. Now this line is 5. So 1 decade means 5 into 10, that means 50. That's why I have considered over here that is 20, 30, 40, 50. This line is 50. So next I will join it by dot line, as the corner frequency is occurring before this point. So up to this part, next corner frequency 10, this part is solid line and remaining part is dotted line. So this part is the minus 40 dB per decade, and this is the next corner frequency, that is 10 radian per second. And after 10 radian per second, then the slope has been changed into minus 20 dB per decade, and this minus 20 dB per decade will continue till the next corner frequency 20. So here again I have drawn from the next corner frequency 10, I have drawn the minus 20 dB per decade slope. So minus 20 dB, that means to the downward direction I have to go only 5 units, then 1 decade. So this represents dB, and in x-axis we need to consider the decade, that is 10 into 10, that is 100, and then it gives the minus 20 dB per decade slope. And this slope will continue to the next corner frequency 20 radian per second. So there are 3 corner frequencies, and each corner frequency the slope has been changed. So this one is minus 20, then this is, that is minus 40, and again minus 20, then the minus 40 dB. This minus 40 dB, there is no more corner frequencies, that means this minus 40 will continue up to infinite. So that's why at the last point I have drawn the minus 40 dB per decade, and it has to be going to the infinite. So from this is the magnitude plot, and from this magnitude plot we can see that the magnitude plot cut the reference line 0 dB line at 10. So the gain crossover frequency is 10 radian per second. Next is the phase plot. And phase plot, it is very much simple. In each omega value, this represents the omega values. So for each omega value, we will put the degree values. So for 0.1, the value is minus 89 point something. So then at 0.4, so from this graph, this is minus 93.42. So this is minus 93.42, and I have chosen that its small box in phase plot, that is equal to 2 units. So after 5 boxes, that is 10 units I have considered, and you can vary this as per your choice. So I have considered for the phase plot, one small box represents 2 units. So in this way I have plotted all the points, and this is the phase plot of the open loop transfer function. Now we can see when the value is infinite, then the angle value is minus 180 degree. That's why in this graph I have not cut the reference line. The last line is the reference line, and this phase plot does not cut the reference line. So there is no phase crossover frequency. That means phase crossover frequency will occur at infinite value, because it at infinity the value is minus 180. So before that infinite value it will not cut the minus 180 degree line. So this is the conventional way to draw the bode plot. Let us take another example. Here in the same way, first I have converted into a sinusoidal transfer function by putting s is equal to j omega. Here I have not considered the first step because it is already in the time constant form. So I have just started from the sinusoidal transfer function, that means put s is equal to j omega. And in the same way, the value is depending on the 1000 divided by omega, that is the pole at the origin, and the constant term. So it becomes, and omega is equal to 0.1, so it becomes 80 dB. So the graph will start from the 80 dB. So here there are 4 factors. For 1000, the corner frequency is 0, and so slope contributed for 1000 is again 0. Net slope will be 0. And then we will write the 1 by j omega term. The corner frequency for 1 by j omega is 0. Slope contributed is minus 20 degree, dB per decade, because it is located at denominator. And the net slope is the summation of the current slope and the previous slope, that gives us minus 20. Next, we will find out the two more corner frequencies, that is 1 by 0.2 and 1 by 0.1. So 1 by 0.2 gives us 5, so that is less. So it will come first. So 1 plus 0.2 j omega has been considered the third factor, and for this corner frequency is 5. And for this corner frequency, the slope for this term, the slope contributed will be plus 20 dB per decade, as it is a numerator term. And the net slope will be this minus 20 and summation of this plus 20, that gives us 0. And for the last term, that is the 1 by 1 plus 0.1 j omega, it is located at the denominator, and the corner frequency is 1 by 0.1, that means 10, and slope contributed for this factor is minus 20 dB per decade, and the summation of the previous slope 0 with this minus 20 gives us minus 20 dB per decade. And for the phase plot, the angle the formula becomes minus 90 minus tan inverse 0.1 omega plus 0.2 omega, and omega is varying from again 0.1 to infinite. Here we can see that when the value is 0.1 omega value, then the angle value is minus 89.4, and then it will decreasing, actually increasing because it is in minus, so it is increasing, and then at infinite the value is again decreasing to the minus 90. So this one is the graphical plot. Here again I have started from 0.1, 1, 10, 100, 1000 and 10,000. So these are the decades, and this one is the reference line, 0 dB line for the magnitude plot. And for this magnitude plot, again I have considered one small box is equal to 4 units. So after each 5 boxes, you can mark the 20 dB, 40 dB, 60 dB, and final this one is 80 dB. So the graph has been started from 80 dB because starting point was calculated as 80 dB. And then we need to consider this table where from the starting point 80 dB, the slope will be minus 20 dB per decade up to the corner frequency 5. So the slope has been plotted just like the previous example, that is here minus 20, that means we have to go downwards 5 boxes because each box represents 4 units, and then 1 dB. So if you join these two lines, then you will get minus 20 dB per decade slope, and it will continue up to the next corner frequency, that is the 5 radian per second. And at this corner frequency, the slope has been changed into 0 dB per decade and it will continue up to the next corner frequency 10 radian per second. And then again in the same way, I have drawn the minus 20 dB per decade, and it will go till infinite with the same slope. And this magnitude plot cut the 0 dB reference line at 2000 radian per second. So the gain crossover frequency is 2000 radian per second, because this is 10,000 and then the next two represent the 2000. So the gain crossover frequency is at 2000. For the phase plot, here I have chosen the same. This is minus of 70 degree, and each box represents 2 degree. That means after 5 box, this is 10 degree. That means minus 70, minus 80, minus 90, like this. Because from this relation, we can find out that at infinite the value is minus 90. So there is no necessity to draw the minus 180 degree line, because it will not cut the minus 180 degree line. So I have just taken from minus 70 to minus 110. And like the same way, in each values of the omega, I have plotted the degree values and then got the phase plot curve like this. And it has not cut the reference minus 180 degree line. That's why there is no PCF over here. Here also PCF is equal to infinite. So in this way, we can easily draw the bode plot of each factor, and then cascading them all, we can find out the overall open loop transfer function bode plot. And in the next video, we will find out the gain crossover frequency, phase crossover frequency, and the phase margin and the gain margin to find out the stability of the system. Now the phase margin and gain margin are nothing but in this term we will express find out the relative stability. The phase margin and the gain margin both has been discussed in the using the polar plot. You can easily find out the phase margin and gain margin using the bode plot also. Actually, in bode plot, a vertical line has been drawn from the phase crossover frequency point and of the phase curve up to the magnitude curve, and the gain margin is dB is obtained. And in the same way, you can find out, draw a perpendicular from the GCF, and then the difference between minus 180 to phase plot, that gives the phase margin. So we will discuss all these stability criteria in this next video. These are the references. Thank you.